Systems of linear inequalities. We're asked to graph the system of inequalities. Y is less than 1/3 x minus 2, and 2x plus y is less than or equal to 5. So what we're going to do is graph each inequality and graph both of them on the same grid, and then we're going to look for a solution region. And the solution region is going to be the set of all ordered pairs that satisfies both inequalities. For the first one, the graphs are already drawn for us, so let's label these. This solid one is 2x plus y equals 5, and the dashed one is y equals 1/3 x minus 2. Remember that when we have a strict inequality, that line should be dashed, and when we have an inclusive inequality like this one, that line should be solid. We learned this when we learned to solve single inequalities in two variables. The only difference here is that we'll be doing two of them together on the same grid, and we want to come up with one solution region to shade. That is the solution region for both inequalities. So what we're going to do is, again, start with a test point, and since neither of these lines goes through the origin, 0, 0 is going to be a very good test point. And I'm going to plug it into both inequalities, one at a time, and see if it satisfies them. So starting with y is less than 1/3 x minus 2, I'm going to plug in 0 for x and 0 for y, and I get 0 is less than 0 minus 2. So 0 is less than -2. This is a false statement. 0 is greater than -2, and therefore from the line y equals 1/3 x minus 2, I want to shade away from my test point. I'm not going to start fully shading just yet. What I'm going to do is draw arrows in the direction that I would shade if I were just graphing the solution set to this one inequality. So I would shade away from the origin, which means in this case I would shade down. Now I'm going to go to the second inequality. 2x plus y is less than or equal to 5. I'm going to use the same test point 0, 0, because I can use any point that's not on the line. So as long as the line doesn't pass through the origin, this is the easiest one. This gives me the statement 0 is less than or equal to 5, which is true. So I'm going to shade toward my test point from this line. Again, I'm just going to draw the arrows for now that indicate what direction I would shade. From this line toward my test point. Very important to label the equations of the lines so that I don't have to be figuring that out again, which line is which, each time I'm going in to draw these arrows. Now to figure out what my solution region is, it's going to be the one that has arrows pointing into it from both lines. We can see that if we look first at this sort of upper left, the largest region, it has one arrow pointing into it, but not a second. So that's not our solution region. And it looks like the one on the bottom is the one that we want to indicate. So I'm going to shade in this region on the bottom that has two arrows pointing into it. Going on to the next example, it's going to be the same idea, but this time we are drawing the graphs ourselves and doing the whole thing from scratch. Go ahead and pause the video if you want to try it yourself before seeing my solution. I'm going to start by graphing the line y equals 2x minus 1 as a dashed line because we have a strict inequality. So this is going to be a slope of positive 2 over 1 and a y-intercept of 0, -1. So starting at my y-intercept, using a slope of positive 2, put together these points and then draw the line that passes through them. Next, going on to the equation, x plus y equals 5. This will also be dashed. I would probably do this one by intercepts, although it certainly works to do this by y equals mx plus b as well. But note that if x is 0, then y is 5, and if y is 0, then x is 5. So we can very quickly get 2 points that are on this line, and then draw the dashed line that passes through them. Again, I need to find a test point for each line. I don't have to use the same test point for both lines, but the point 0, 0 does happen to be off of both lines, so we can use it. So I'm going to plug in 0 for x and 0 for y in both of these inequalities, starting with y is less than 2x minus 1, which was my first. Let's label this as y equals 2x minus 1. Plugging in 0 for x and y gives me 0 is less than negative 1, which is false. So from this first line, I'm going to shade away from 0, 0. Using the same test point for the second inequality, which goes with the equation x plus y equals 5. My second inequality is x plus y is greater than 5. Plugging in 0 for x and y gives me 0 is greater than 5, which is also false. So for both lines, I'm going to shade away from 0, 0. And from this line going kind of up and to the right is away from 0, 0. I can see that this region in the upper right looks like the one that all of my arrows are pointing into. So now I'm going to fill that in. So this is the region in the upper right that we're filling in. As our solution region.